please give a warm welcome to Hannes Hapke.
I have to start off the presentation with two bad news. Number one, I'm not Amy. I'm sorry. If you were looking for Amy's presentation, you just have to wait 30 minutes and then Amy will be there. And then the second bad news is most machine learning models are not getting deployed. That's a fact. And there are a million reasons for that. But the key reason is that most people think that it's way too difficult to do that, way too cumbersome, there are too many moving pieces. But I want to prove them wrong. And in the next 30 minutes, I want to show you how you can deploy your machine learning models in 90 seconds. My name is Hannes. I'm currently the head of engineering at a small startup in Portland, Oregon. We develop machine learning models in the natural language processing space. And the company is fairly small, so we have to automate a lot of the things around our machine learning pipelines, including the way we deploy machine learning models. And so I can't sit there and work, write some Flask code for like 2 days and build containers by hand and stuff like this. So this talk is all about how we automate things with TensorFlow Serving and how you can get out your machine learning models in no time. Let's face it, the deployment of machine learning models is basically what stands between you, your hard work, your model, and the outside world. And if people want to use your models to make predictions, to classify their own data, you have to deploy it. So that's why the deployment of machine learning models is important. But I'm often getting asked when I present this to data scientists, why should I care about this? We have a DevOps group. There are software engineers. They can do this so much better than me. Well, I think it's the responsibility of the data scientists right now to make sure that your hard work is getting deployed and is being usable by the outside world. And the reason is currently we have these two fields where we have the data science side and the machine learning side, and then we have a DevOps group, the DevOps side on the other side. But they're currently sort of merging, and while new job descriptions are emerging, it's the responsibility of the data scientists to get the models out. The reason here is the DevOps people are really great at scaling applications. They're awesome to go from 10 users to 1 million users. They're wonderful at setting up Kubernetes environments to really have like a seamless deployment process. But they're not the experts in the machine learning ecosystems like TensorFlow or PyTorch. And the way we deploy machine learning models, these tools are always coming from the machine learning side. So it comes down to you guys, the data scientists, the machine learning engineers, to drive that process, to come up with a POC, and then go back to your DevOps group to say, hey, this is how we do this on our local machines. Can you scale this, please? So before we get into all the details of like deploying our machine learning models with TensorFlow, I want to show you a highly inefficient way of deploying a machine learning model. This is an example here what you will find on various blog posts. And this is a completely legitimate way of deploying it, but it's highly inefficient. So the way it works is you load a Flask application. You can use Fast API or Django or whatever you want to use to generate an API instance. You get some data in from some user. In this case, we have a form. You pre-process it. Well, the pre-processing is a module. I just import this. And then we make a prediction. Whatever the result is, we turn this into a JSON response and reply this back. What's the problem here? So the problem is, well, this is using a sort of a Python package which is meant to use or meant to work with HTTP responses. It's not designed to use your hardware to make predictions efficiently. So in this moment, when you call predict, you basically lock up your CPU or your GPU for this one data sample you just got from this one user, and then everybody else has to wait. So the other problem is, since you write your own Flask code, the next project I'm writing tomorrow could be completely different. Could be a completely different URL structure. The payloads could be very different. I could do the versioning very different. So onboarding new team members is just horrendous in this setup. You're losing out on the capabilities of mini-batching. We'll talk about this in a little bit later, what it is and where this really shines with TensorFlow. And in the Flask setup, it's really difficult to load large models. So if you want to deploy like a universal sentence encoder, when you deal with like gigabytes of weights, that doesn't really scale really well in Flask. So that's where TensorFlow Serving comes in. Very quickly, if you run this in Python, It looks like this, your entire setup. So it works, but it's just really hard to maintain. Yeah? So let's talk about TensorFlow Serving here. So TensorFlow Serving is part of the TensorFlow extended ecosystem. TensorFlow itself has some tools around it, where the tools are going to help you in terms of data validation, model analysis, and as part of that ecosystem, there's also a package for serving machine learning models. It's battle tested, has been used within Google for many years. It scales really nicely. It works together with modern Docker setups and Kubernetes setups, and you can serve models easily up to 2 gigabytes of size limit. The reason why we talk here about 2 gigabytes is everything has to be converted into a protobuf format, and that has a 32-bit limitation, and that ends up with 2 gigabytes. Before we get into all the detailed settings, the one thing you need to do is you need to export your model. So let's assume, like what was showing earlier, you trained a model, you're done with your training, you have done all your analysis, you're good to go for that model to be deployed. In this case, you can call that tf saved model.save method, and that method will export the model in a very structured way. It's a slightly different function call what you saw earlier in the other presentation, because what we want is a very standardized format here, where the model is being exported with the timestamp, which is unique to the moment when you exported the model. And then the data structure underneath that folder is always the same. So the model graph is being exported as a protobuf representation, as a saved model.pb file. And then all the variables, all the checkpoints, they can be found in the variable folders and assets folders and so on. With this, you can very easily then just run 2 commands. Basically docker pull, and you pull the image from the Docker registry. And then you start up that Docker container, which is already pre-configured, with the arguments here. So in this case, we're just opening up 2 ports. We're exposing these 2 ports. We're mounting a folder where we exported the model to. And we tell the TensorFlow Serving instance inside of the container of where to find that model. And then we pass in the environmental variable of like, hey, this is the model we actually want to looking for, or we want to serve. In this case, it's called my model. And then we use the image of TensorFlow Serving. Sometimes you want to run your inference on a GPU. The only thing you need to change is the last line. You basically need to use a different Docker image, which has all the NVIDIA and CUDA setups, and then you're good to go. And then when you see this, when you start it up, you're going to see these outputs. And what you want to look out for is that everything was successfully loaded, and that you have 2 services running, one at 8500 and one at 8501. And we talk about this in a second, what it is. So in the previous setup I was showing you, and I think you can do this depending on your internet speed, but you can probably do this in 90 seconds. That's a full deployment. You're done. And sometimes you just don't want to copy your models through SSH into the host machine, so you can easily link your TensorFlow Serving instance to a remote folder, which could be any major cloud provider, Amazon, GCP, whatsoever. And the only thing you need to change is the way you instantiate your run command. So in this moment, instead of mounting the local folder, you just point it towards that S3 bucket in this case. Side note, you have to put in you have to sort of deal with the credentials, but let's assume that your container knows the credentials, or you can sort of expose them this way, then you can load them in Docker. So the previous configuration I showed you, that works with one model. And the standard policy in TensorFlow Serving is that whenever there's a newer version showing up, the old model is being unloaded, and the newer version is being loaded. So that's a pretty wonderful setup. If you want to configure 2 models, there's an easy way you can do this. You just basically create a text file, you use this data structure from this slide, and you define the name of the model and the base path of each model. And then once you do that, once you're done with that, you mount that configuration file into the container, and you basically tell Docker run where to find that configuration file. That's it. And all of a sudden, you run 2 models in parallel. It's not something I would recommend for a production setup, because since you're using containers in that moment, you might want to scale different models at different rates. So if you have a very popular model, you want to scale this differently than an infrequently used model. If you lump sum them together in one container, you basically lose this ability, and then you basically lose a lot of memory. So scaling differently would be good. But what you can do is serving multiple versions through the same container. So in this case, you want to serve two versions of the same model. Maybe you want to do A/B testing. And just by configuring the policy in your configuration file again, just 4 extra lines, and you're good to go. And the numbers you see there is basically the timestamp from your export. There's also this wonderful setup. You can configure labels for each timestamp. So it's always hard to remember what timestamp was it, what was the stable model, what was the testing model like. Yeah. Just use the setup here if you want to configure labels, and then you later on in the inference step, you can infer based on the labels. So now, since we're done with the TensorFlow Serving setup, you basically just deployed your model here. Let's talk about how you can predict, or how you can use it for your predictions. You have 2 ways you can access this model. You have a GRPC, which is Remote Procedure Call protocol, and you have the REST protocol, which is running on, they're running on 2 ports, 8500 and 8501. Initially, TensorFlow Serving was released just with the GRPC protocol, because that's what Google is using internally. And then later on, a lot of people wanted to use it in the REST setup, and it was released with the REST implementation. Let's quickly talk about the REST implementation and how you can infer your models. So the URL data structure is always the same. So basically, you have a host, you have a port, and then you point it towards the model. And if you don't specify a version, like what I'm showing in the example below, then it always will go to the default model, which is the latest one. That's the default behavior. So let's say you use Python on your client side and you want to quickly infer your model. This will be the code you can do it with. So in this moment, you basically have to generate the URL path. In this case, it's my local machine, my model, it's loaded. I create like a JSON data structure. Everything is running under the key instances, and then I provide a list of my data samples. In this case, I only have like 1 item. If you have a multi-input node model, then your list would contain dictionaries with the names of the input nodes as a key. And then I make a post request to that API. And whatever I'm getting back, I can return this in this function. And the return in that moment would be my prediction result. So you might ask, like, how does it work in the gRPC environment? That requires a lot more code, and I don't want to spill the code all over the presentation here. So I just want to walk you through conceptually how this would work. So earlier you saw that we had like a data structure, and we converted that into a JSON format. In the gRPC environment, you would have to convert this into a protobuf format, which is basically representing the TF examples data structure internally. So in that moment, you have to convert each field into its data types. On the client side, you say, this is maybe a string if you work on an NLP problem, or this is a number of floats or integers, et cetera, et cetera. Then you convert this into a base64 representation. And through a gRPC stub, which is basically handling all the communication with the server, there are methods on it where you can predict the individual examples. So often the question arises, like, should I invest all the extra time of coding to get the gRPC to work, or should I just go with simply and straight with the REST implementation? And I would say, if you just want to get something up and running, REST is totally fine. It's easy. It's easy to debug. You can use it in your browser. You can use curl commands. It's pretty straightforward to infer your model in that moment. However, if you're interested in reducing your bandwidth, if you have to shuffle a lot of data back and forth, if you're interested in like fast inferences, you might want to go with the GRPC protocol. It doesn't work always. It's not always faster than REST, but in a lot of cases it is faster. You definitely save a lot of sort of bandwidth if you shuffle data back and forth. And it might be faster because if you submit it as a JSON data structure on the REST endpoint, then the server has to go in and figure out like what data type is each field, and that just takes time. On the on the GRPC endpoint, that's all being done already on the client side, and the server doesn't have to figure this out. Earlier I mentioned you can use the TensorFlow Serving instance to perform A/B testing. Well, the bad news is TensorFlow Serving doesn't really support A/B testing. It doesn't do it. It can't do it on the server side. However, you can very quickly compile A/B testing capabilities from the client side. So you just need a little function here where you define your URL data structure. And you can basically, if you have two versions you want to test, you just generate two different URLs for your inference endpoint. And then whenever you want to infer the model, you have a little a random number generator. If the number is below a certain threshold, you just infer to one endpoint. Otherwise, you use the other endpoint as a default value. And that's a quick and dirty A/B testing. Sometimes you want to know information about the model on the client side. So that often happens in mobile applications where you might update your machine learning models more frequently than your iOS app or your Android app. But let's say in your Android app, you want to know what model did I just infer with, or what is the architecture inside of the model. TensorFlow Serving provides you an endpoint where you simply use the same URL data structure, you append metadata to the URL structure, and you just make a GET request. And once you do this, this is what you get back. This is basically my model in this moment. I see when I exported it, and I see all the inputs and the outputs, what data type they are, what type, what's the shape, et cetera, et cetera. So up to this point, everybody can tell me that's like, yeah, sure, you can do this in Flask. It takes a little bit more than 90 seconds to code, but generally you could do that. The next feature I want to show you is something you can probably, I don't think it's not efficient to do that in Flask. Let's say it this way, and that is sort of mini batching or batching your inferences. And that's a wonderful setup and a key feature of TensorFlow Serving. It's a little bit underrated in the documentation. Somehow it got missed when the documentation was written. But it's wonderful to sort of compile a bunch of requests towards your model and then batch them together and use the exact same process what we normally do in our training instances during your prediction phase. So let's say you have a computer vision application. You can gather a bunch of images, and since everything runs on a GPU, you can parallelize everything in that moment and compute everything together. And then TensorFlow Serving handles all the responses to the individual clients in that moment. So this would be the setup. Basically, all the different clients would submit their results, submit their inference data to TensorFlow Serving, and then all of a sudden, sort of everything would be compiled as a batch. And then once this is done, it gets returned. The only thing you need to do is this. You need to configure a little text file here where you say, this is my batch size, and this is my max timeout. So in this moment, you basically say, hey, wait, this is the maximum amount of time you should wait, or my batch is full, and then compute it anyway. And with this text file, you can then add it to your TensorFlow Serving configuration simply by appending it to your Docker run command. I just want to point out one thing that is you should be careful with like the settings in this moment, because if you want to make a batch process or batch computation, you want to have a large timeout. You want to use your batches efficiently. When you use it in the context of like real-time applications, in this moment you want to have a very short timeout cutoff. So, but for most applications, you're somewhere in between. Like you can wait maybe 200 milliseconds, maybe 100 milliseconds, but it's very application dependent, and you should just try and error the two settings there. All right, I just want to point out a couple more optimizations for your server, and I really want to highlight the first one here. By default, TensorFlow Serving checks your file system every 2 seconds if there's a new model available or a new version is available, and then it does the unloading process or the loading process. If you connect this to a remote folder, and TensorFlow Serving is basically checking every 2 seconds that remote folder, and maybe let's say that that folder has like 1,000 versions of your model in there, you generate a lot of network traffic. And very quickly, you see a nice monthly bill coming in just from polling this every 2 seconds. So in this moment, I would highly recommend use this setting, set it to, I don't know, 120 seconds or something. It's totally fine to check every 2 minutes, I would say. But don't run with the 2-second standard behavior. All right, again, if you want to use one of these additional settings, you know the drill. Just add it to the Docker run command, and you're good. These days, our models are becoming bigger and bigger in the computer vision field. They can be easily large amounts of megabytes or gigabytes. In the NLP space, we have universal sentence encoder where we quickly reach a gigabyte, and nowadays we're talking about BERT and ExoNet and things like this. So very quickly, you need to probably optimize your model in terms of computation. And you have 2 ways you can do that. You can either prune your model, or you can quantize it. And there's a really nice way to apply quantization to your TensorFlow models by using TensorFlow RT, which is a functionality provided by NVIDIA. So in this moment, you basically reduce the precision of your model from a float32 implementation to something which requires less, like float16 or int, less memory space. So in this moment, your model becomes smaller and your computation is faster. And you can do this very quickly by using Safe Model CLI. That's a wonderful TensorFlow serving tool. It not just allows you to convert your models, but it also allows you to inspect the models in the command line. You can run example predictions just from a terminal. And then you add this again to your Docker run command. You have to load the runtime NVIDIA engine, and then you point it towards the path of the quantized model. And since it's NVIDIA, it has to run on a GPU. I'm sorry, but that's the condition. If anybody here is using PyTorch, just one slide for you guys. It's almost impossible to use TensorFlow Serving with PyTorch. And the reason is TensorFlow Serving uses TF example under the hood. And I don't think there's any connection between PyTorch and TF examples existing. That's sort of the requirement to use it in the setup. But there is Onyx in the PyTorch world. And Onyx is a way to it's a standardization of neural network exchange formats. But Onyx also comes with its own runtime engine. So it has like a server, and it has like similar to TensorFlow Lite and TensorFlow JS. You can run it in the browser and things like this. So if you want to deploy your PyTorch models, take a look at Onyx. And then just want to give a little outlook of where we are in terms of like the machine learning infrastructure field, what's going to happen. We're going to see more and more deployments to edge devices and browsers. That's going to change our deployment process. We were seeing more and more tools like Kubeflow, where we basically build entire pipelines where we can sort of automate our machine learning workflows. So it's not just about serving, it's about data validation, data cleaning, or data pre-processing, model validation, and things like this. And then we have the field of like federated learning, which has the potential of changing the way changing the way we think about machine learning deployments. In this case, we would basically not deploy it to a central server, but the model goes out to the sort of edge devices, but then they talk back to the central server, and they get sort of the updates of the weights. Just want to, if you're interested in this field, a wonderful colleague of mine, Catherine Nelson, and I, we're right now compiling all the different stages of a pipeline, of a machine learning pipeline, and we're compiling this O'Reilly book, and we're looking forward to an early release around TensorFlow World in October. And with that, I'm happy to take any questions, and thank you.